come somewhat in the middle of the course right now. So what we have covered so far is basically simulation based verification. So we talked about how a simulator works, then we saw how to develop test plans, how to define coverage of the test plan, and then we also looked at assertions, which is also a part of the verification environment. We looked at layered test bench architectures. So now today what we are going to do is to study a particular case study which is going to talk about this whole framework in the context of one example. Okay. So the example that we have chosen here is the AMBA APB. So AMBA is a advanced bus architecture for the ARM processor, and the ARM processor has two types of buses, the advanced AHB bus and the APB bus. So I am going to describe what these two buses are and what is the total ARM architecture, and then we are going to study this protocol in more details and see how we can build a verification environment for this protocol. So this picture shows the complete architecture of the ARM processor. So we have the high performance ARM processor here, and we have the high bandwidth memory interface, the on chip RAM, and the DMA bus master. These are the components which are sitting on a high performance bus. So AHB or ASB is the high performance bus. In other words, that this bus has higher bandwidth than the bus on this side. So there is a bridge between the bus on this side and the bus on this side, and on this side we have the APB, which is called the peripheral bus of the AMBA bus architecture. The peripheral bus, as the name suggests, is used to connect the peripherals to the architecture. Okay, so peripherals like the UART, the timer, the keypad, okay, these are all part of the low performance bus. Okay. So if you look at this side of the thing, then there is only one master device. The master device is the bridge. Okay. So all transactions etc. are initiated by the bridge. Now the bridge obviously cannot initiate transfers on its own. So it is one of these devices which is actually initiating the transfer through the bridge. Okay. And then once the bridge initiates a transfer, then these are slave devices and they communicate to the master through the slave. So at a given point of time, the APB bus is used to communicate between the bridge and any one of these devices, right. And this is typically the architecture that you will see in any bus architecture for any processor, because the bandwidth of the processor with the memory has to be the maximum. So typically people use high performance bus on that side, and you use low performance bus on the other side. In the Intel architecture, for example, there is a north bridge and a south bridge, okay, and in the north bridge you have the processor and memory connected, in the south bridge you have the peripherals connected. So it is the same thing, you know, just using different terms. So the three components that are there in this architecture are the advanced high performance bus, which is called the HB, the advanced system bus, which is called the ASB, and the advanced peripheral bus, which is called the APB. And this is a very commonly used architecture, because as you might be aware that ARM processor is one of the main on-core processors that people use for developing embedded systems. So if you want to develop a chip for an embedded system and you need a processor, then ARM is one of the very strong candidates for your use inside the as an on-core processor. Okay. So this is the APB state diagram. So as I had mentioned in one of my earlier lectures, that mostly for the protocols you will have an abstract state machine, right, and then in each of those states there are some more things which are happening. So the abstract state machine here is defined in terms of two signals. So that is the P cell X and P enable 0. Now P cell, the X stands for the device which is selected. Now if you go back to the architecture, you see that the bridge has to select one of these 4 devices, right. So, there are independent lines for that selection, right. So, P cell 1 may be selecting this one, P cell 2 might be selecting this one, right. So, when we talk about P cell x, it is one of those P cell x. So, if that is 0 and P enable is 0, then it is in the idle state. Okay. When it wants to start a transfer, then it will raise the P cell for one of the devices. That is what the bridge is going to do. Okay. It is going to raise P cell 1 or P cell 2 depending on which device it wants to access. So, that is the setup phase, and then it will raise the P enable, which is only one signal, it is not P enable x, P enable is one signal. It will raise that, and that is going to initiate the transfer. Okay. So, that will initiate the transfer of one data, and then it can go round and round in this loop several times to transfer several data items, okay, for the same device. And then when it is done, it is going to lower both P cell x and P enable and go back here, right. And while it is doing several transfer, P cell x remains high and P enable toggles to 0 1 0 1 0 1 for each item of data that is transferred. So, there are some salient features of this. This is just for your information, that this has low power consumption, reduced interface complexity, latched address and control. So, that means that when you float the address or float the control signals, they are latched at the output of the interface, right, so that they are held steady, and it is suitable for many peripherals.
Sir, P enable you said is for initiating the transfer.
P enable is going to be raised for each item of data that is transferred. I am going to show you a transfer now in detail. So, that way you will be able to see exactly what is happening.
And what was the difference you said was between the states, what is the state, the setup and the one below that?
The setup and enable?
Yeah.
Okay. So, setup is, see, when you start the transfer, you first select the device, and then for every item of data that is transferred, you raise P enable. Once the transfer is done, you lower it, then again you raise it to send the next data item. So, you see, this is where the address is being floated, this is where the data is being transferred, right. So, that is how it flips. Let us see an actual transfer, we will get the picture very clearly. Okay. Now, this is the interface, this is the bridge interface. Okay. So, it has two sides. This side is for interfacing with the high performance bus, and this side is for interfacing with the low performance. So, we are APB is on this side. Okay. So, we are going to look at this side only. So, on this side you see that these are these n select lines for the n devices. Okay. There is a single P enable, this is the address bus where the address is floated. Now, since every transfer is initiated by the bridge, this is the only master. So, you see ADDR, the address is floated always by the bridge, okay, because it is initiating the transfer. Whether to read or to write, it is initiating the transfer. Okay. And then P write is the signal which is used to write or read. So, this tells you whether the transaction is a read transaction or a write transaction, and this is the data bus. Okay. So, this is the data bus which will be used to read when the transaction is read, and will be used to float the data when the transaction is write. Okay. Now, this is the slave side. So, this is for one of those peripheral devices. So, it receives its, so this is the APB slave X. Okay. So, it gets P cell X, which is the select line for this device. It gets the P enable. P enable, mind you, is going to all the devices, the same line is going to all the devices. It receives the address, it receives the P write signal. There is a preset N, which is a reset pin here, okay, which can be used to reset the slave. This is driven by the controller, not by the APB. Okay, this is driven by the global controller, and then you have the clock. This is the clock for the slave, and there is the data bus. Okay, so this is the slave side of it. Okay. This is a write transfer. Now let us see what is happening here. So first thing is that the master will raise P cell. Now see, this is where it is raising P cell, okay, and at the same time it is floating the address. Okay. So the master is doing the two things, it is raising P cell and floating the address. Now at this point, let me choose the pen. See, it is at this point that the slave sees that the P cell is high. Okay. Remember that everything is sampled here, right. So it is at this point that the slave sees that the P cell is high, so it also gets the address. Okay. Now this is for a write transfer, so the data is also floated in the same time. So see what has happened here, because this is a write transfer, so the master, which is the bridge, raised the P cell, floated the address and also floated the data, because it is going to write, it has the data, right. Now when the slave gets these three, okay, it gets time up to the next clock pulse to latch in the data, to save the data, okay, and in the next clock pulse P enable is raised, right, and when P enable is raised, the data is latched by the slave, right, and in the next cycle the master can take that data away and put another data, right. Similarly, if the master wanted another transfer, then it could float another address here, right. But see, the interesting thing here is that P enable goes high here and will go down here, okay. If there is another address being floated, then it is going to get latched in the next cycle when again P enable is raised. So there is one cycle gap between the data transfer. Is that clear?
Who is driving the P enable?
The master. Each of these are being driven by the master. There is only one master device and every other device is a slave device. Okay.
So they are giving only one clock cycle for the slave to be allowing no delays in the slave.
No, this is not like PCI. See, in PCI the master waits for the slave to be ready. So there are signals like IRDY where the master waits for the slave to be ready, right. Here it is assumed that the slave will be ready, right, in the APB, right. So if for example the slave is not able to produce data and produces some garbage, then that will be taken up in the higher layers of the of analysis, where something like CRC check might fail or things like that might happen, okay. But at the bus level it is assumed that there is no wait here. On the high performance bus side, on the AHB side, there is provisions for this. On the high performance bus side, it is possible to for a slave to split the transfer in case it is not ready. This is the picture for a read transfer. Now see, the difference here is that when it raises the P cell, at that time, see here the P cell has been raised, but at that time it can float the address from where it wants to read it, okay, but it does not have the data, because data is going to come from the slave, right. Now what does the slave do? When the slave sees that P cell is high, P cell for it is high, and then it uses the address and gets the data out. So it at this time it sees that the address is there, P cell is high, so it reads the corresponding address and floats the data in the PR data line, okay. Now once this data is available, in the next cycle the master raises P enable and reads the data, okay, and then lowers P enable. So you see the next data cannot be put in here. I mean, even if it is put here, it will not be read in the next cycle. It will be read in the cycle after that. Why? Because P enable is going down, then in the next cycle P enable can go up, and in T6 it can read it if there is another data item. Okay, right? So is this clear roughly what is taking place? Now let us see how we build a layered random test architecture for the APB. Now just to recap, this is the layers that we talked about. The driver layer is the one which is actually driving the signal. So that is the absolute lowest layer, the signaling layer, where the actual signals are being toggled. And then there is a sequence in which those signals will have to be toggled, like P enable going up, P cell going up, then in the next cycle P enable going up. So this sequencing is done by the transaction layer. So it is the one which is actually going to drive a read transaction or a write transaction. Okay. So given that I have to perform a read transaction, the sequence of actions like raising P cell, then floating address, this is done by this layer. The layer above that decides that whether this is a read transfer or a write transfer. So it chooses between the transfers, right? And the layer above that says how many transfers should I do. Okay. So this is the layer where you decide about the high level set of tests that you are going to do. This is the one which randomly generates a test in that category, in each of those categories, and then this is the one which executes that transaction, and this is the one which raises the signals at the interface level. Question is, how do these layers communicate? So these layers communicate by things which are called channels. Channels are like pipes. You may think of these as individual processes, and there are pipes through which they are sending in this thing. So I randomly decide what is the transaction and push it into the pipe. This one reads what the transaction is and executes it. Okay, so that's the way in which this is going to work. Okay, and then that's going to be the interaction between these two layers, between the duty and the driver. The monitor will study this interaction and similarly pass on the interaction to the checker, and the checker will also know what transaction is being given. It will know what is the outcome of that transaction, and the self checking environment will check whether what we are expecting is what we have got, right? And assertions are going to be part of this self checking environment, right? Is that clear, the setup? Just to recapitulate. Now let us get into this thing. So this is that same thing, supplies data to the duty, executes the transactions. This one creates random transactions. This one creates interesting conditions. This one observes data from the duty. This one identifies transactions, and this one checks the correctness. Okay. Now this is the top level thing that we do. Okay, I am starting from the top, and then we are going to dig into each of these things. The whole thing is going to run in the initial block. Now in the system Verilog test bench, it is in this initial block that we call these tasks, and once these tasks are executed, we are done. Right? There is nothing else in the test environment. Everything is within these tasks. Okay. So the first one is a constructor, as you can see, new master. MSTIF stands for the master interface, MONIF stands for the monitor interface. So it constructs this, okay, and then we do an env.build, which is, I am going to tell you what this does, and then we are going to do env.run. Env.build is the one where we initiate the transactor, we initiate the generator, we initiate all these different layers and connect them through channels. Okay, that's where we create the we construct the channels using again new operator. So the channels are a class. Okay. So in system Verilog test bench architecture, you can have classes defined. So the channel is one class. So you can instantiate instances of the channel and then connect the channels with the different transactors. I am going to show you how, and then that completes the building of your environment. Then when you do run, then it actually runs that entire set of tests. Okay. So let us see this one. These are the components. Okay. These are the components which are going to be created and linked up when you call the env.build. Okay. So we have the APB CFG, which is the transaction configuration. Okay, this is a configuration file. Let us not worry about what it contains right now. This is the channel between the generator and master. So APB trans channel. Okay, this is a class, and we have this gen to mass. So which is the generator to master channel. Similarly, we have the monitor to scoreboard channel. Okay, the scoreboard is the one which keeps track of the coverage. Okay, so from monitor there has to be a channel to the scoreboard. Then this is the transaction generator. Okay, so this is the APB transaction generator. We are going to see what this contains. Okay, this is where the transactions will be generated randomly. This is the master, this is the monitor, and this is the scoreboard. So these are the low level objects. Okay, this is the generator at one level higher than that. Okay, and these are the channels which are going to connect these together. Okay. Now this is the total stack, the different layers. Okay, and I am just putting in the main functions that are called here. So at the top there is only one random integer. In this case, in this example, at the top I have one random integer called transaction count. Okay, this is randomized to determine how many transactions I will run. Okay, so this is the test layer, nothing more than that. I just decide randomly how many tests I am going to run. So that is given by the trans count, right. Now this layer is going to read the trans count from the channel and then generate one after the other that many number of transactions. Okay, and for randomly generating a transaction, it is going to randomize the transaction object. So for every transaction, what are the things that we need? We need to see whether it is a read transaction or a write transaction, right. We need to say which address it is going to perform the transaction on, and we might say which device it will select. Okay, so things like that. So which device, which address, which transaction, read or write. This is roughly what we need to randomly determine to create one random transaction, right. So these fields will be there in an object which is this. Okay, this dot randomized object, and this dot randomize, just like you have a constructor, this dot randomize is a randomizer for every object. What does it do? If you have an object which has 5 data fields, when you call that object dot randomize, it is going to randomly assign some values to those 5 fields. So it just randomizes the fields of the structure. Is that clear? For any object you can call that dot randomize. Okay. So what this does is that it randomizes the values of that field, right, and then it puts it in the channel. Okay. What is this output channel of the random generator? It is the channel which connects this with the test layer, right, rather the transaction layer. Okay. So and this in the transaction layer, see, it is getting that. See, this is being passed. This is putting it into the channel, and for the out chain of this is the in chain of this. Okay, that is how they are bound. Okay, so it gets this thing, right, and then it checks if it is a write transaction, then it calls the task do write transaction. If it was a read transaction, it would have called the do read, and it passes this tr as the argument. What is this tr? It is a structure containing the address, the device, and the intent, right. So this drives the transaction, this task drives the transaction, right, and when that transaction is driven, this is where the actual signals are driven in this layer. Okay. So we are going to see how those signals are driven. It is going to be driven in system verilog, just by using the non-blocking assignment statements. So let us see in more details now. Is this stack clear? Now we are going to start seeing this thing from the lowest layer of the stack. So at the lowest layer of the stack, we have the interface. Okay, this is the interface definition. So you see this is the PADDR bus, the address bus. Then this is the P select line. This is the interface between the APB master and one of the slaves. Okay. Then you have the PW data, you have the PR data. This is for the write data, this is for the read data. Okay. Then we have the P enable, we have the P write. Okay. P write is the signal which tells you whether it is a read transaction or a write transaction. Now for the slave we have the reset also. Now these are the mod port. Okay, mod port is a construct of system verilog for defining an interface within this interface. Okay, so this is going to do what? It is going to take the whole of the master interface and then say that that is defined here. Okay. See, if you have several interfaces and you want to use those interfaces in the definition of another interface, then you just simply take that and take that as one interface and declare it within the other interface. Now I will tell you why this is useful. Suppose you have a device which is connecting to 2 or 3 different buses, right, and you want to define the interface of that device, right. Now for each bus you define one interface and then instantiate those within the interface definition of that device. So if I am in bus A, bus B and bus C, then I take the interface definitions of bus A, bus B and bus C and put them inside my interface definition for my device. Do you get this? It is just defining the structures within the interfaces. Okay. So that way we have this master, the monitor and the slave. So this is the interface definition at the lowest level. Now this is a do write transaction as it is executed by this thing. So let us see what it does. So initially what it does is that it reads in all this ADDR data write select from the TR. Now what is this TR? TR is the randomized value that is passed on from the higher layer, from the generator. Okay. So now what is this doing? This is first saving that in some structure. Okay. Then what is it doing? It is first after one cycle #1, it is driving APB master interface dot P enable to one tick B1. So that means it is raising P enable. P cell was see, P cell became high here itself. The interface P cell became high here itself. Remember the first step of the write transaction? In the first cycle of the write transaction, we raise P cell. So the interface P cell is raised here. We float the address, we float the data, right. So see, all these 3 things are being happening here, and also we raise P write because this is a write transaction. So in the first cycle these 4 things are happening. Remember the write transaction that we,
But I am little confused.
yes.
I mean, P cell is to select the particular device, isn't it?
Yes.
Then how can it be in just one bit? I mean, without
Okay, so this is P cell X actually. Okay, this is simplified. So in this transaction, in this TR, it will also be mentioned that which device you are referring to, right? And then it is that one. Suppose you are referring to X, then this is P cell X which will be raised here, right? So the select line goes up, the address and data are floated, and P write is 1, indicating that this is a write transfer, right? And then you wait one cycle and raise P enable, okay, and then you lower it in the next cycle. This is the complete write transfer. So the do write is going to do this, right? What would do read do? Do read is going to float the address. This line will not be there. This line will not be there because the data is going to come from the slave. This will be lowered, so it will be 0 tick 1 tick B0, and then this is going to be high, and then it will wait for one cycle, then do this, and also in this cycle it will read the data, right, from PR data, okay, and then it is going to deassert it in the next cycle. That is what will happen in the read transaction. So this is the part of the test bench which is actually doing the read or write transaction. Now let us jump one level upper. So who selects this do write? Okay, who decides whether I am going to do write or do read? So see, this is what the functional layer is doing. This is the layer which is just above this layer. So there it gets the transaction from the upper layer and then checks what this is, and if it is APB trans read, then it does do read. If it is APB trans, if it is write, then it does do write. If it is neither of these, then it does do idle, right? Is this clear? So it reads what it has to do from the upper layer, sees whether it has to drive a read transaction or a write transaction or none, and accordingly calls the appropriate task. One more layer, let us jump upwards. This is a scenario layer, okay. Now let us see what happens here. So we have this APB transaction atomic generator which is constructed here with the initial values of this ADDR equal to 0, this data equal to 0, this DIR equal to idle. This is the construction of the transaction generator, okay. Now what we are doing inside this method for the main of this is we are randomizing this dot randomized obj, okay. Now what does this do? This actually randomizes each of these fields, okay. It randomizes the address, randomizes the data, and randomizes the type of transaction, read, write or idle, okay. Then this is copied into TR, actually not copied, it is called casting, okay. This is cast into TR and then it is written into the channel, right. Now I do not want to get into the nitty-gritties of the language about this cast or this put. So just at a high level you can see that this is what this is doing is that this one is an object which is there with the generator layer, okay. It is an object, right. It randomizes that object and copies that value into the channel. The object remains with itself, so it can again randomize it and again generate another transaction, okay. So every time this is called, it randomizes this to create a random transaction and writes that transaction into the output channel, right, and the layer here reads that and appropriately calls the task, and the layer below that executes that task, right. And what is the top layer going to do? The top layer is going to randomly decide how many tests I want and then call this that many number of times. Okay. So, here we have this. So, this is the test layer. Let us see what happens here. See, we skip the definition of the config, right. What we have in the config is a integer called trans count. It's defined as a random integer. There is a constraint which says trans count is greater than 5, trans count is less than 10, right. When you do cfg.randomize, what is it going to do? It is going to randomly assign some value to trans count which is greater than 5 and less than 10, right. So, any randomization that you do, you can randomize it with some constraints, right. Here this constraint is applicable everywhere, in the sense that whenever you randomize it, it is going to be satisfying this constraint. You can also explicitly call randomize, in the sense what you could instead do is, rather than putting this constraint here, you can say cfg.randomize with trans count greater than 5 and trans count less than 10. Now that constraint gives you the flexibility of using different constraints in different instances of randomization. I randomize the address here with the range this, okay. So I say randomize with ADDR less than this, ADDR greater than this. In some other place in the test bench, I can again call randomize the ADDR with a different interval, right. So that is where we would use the with construct, and this is a generic construct here which is going to be applicable every time APB CFG, this one, and every instance of this is randomized. So CFG is an instance of APB CFG. Whenever I call CFG.randomize, it is going to honor these two constraints, right. So it is going to generate trans count between 5 and 10, and then there will be a loop in which you generate that many number of transactions using this, okay. All right. Now there is the other side of this, where we look at the scoreboard side, right. So from the monitor, there is a monitor to scoreboard channel, okay, and then that scoreboard maintains that what are the coverages that has been done. So in a very similar way, DUT-env creates an object of DUT-SB which implements the checker component, okay, implements check read, check write, etc. Scoreboard waits for a transaction to be generated, then waits for the monitor to notify that this transaction occurred, right. Then determines the transaction correctness by applying the following. Each generated write transactions are stored to a register file which acts as a reference model in this case. Each generated read transactions get their data filled from the register file so as to provide an expected result. Each transaction is then compared on a first come first served basis. So it just keeps a parallel copy of whatever is going on in a register file, right, and it is using that to compare and see whether the expected results were obtained. This is what the monitor is going to do. I will skip the details of this monitor, but you can go through it. The architecture is working in the same way. You have these layers and you have the channels between the layers, okay, and the information gets passed on, but instead of going from the top to the bottom, here it is going from the bottom to the top. Okay. This is also the command layer for the checker. So this was the functional layer for the checker. This is a command layer for the checker. Okay, so that's it. Now what I want you to do, so that gives you an idea about the whole test architecture, how it works, right? The remaining part is the assertions, right? So for the AMBA APB, these are some assertions which I have noted down. So for the P cell, we have a property which says if P cell x is low for some slave x in the present cycle, and in the next cycle it goes high, it must also be high in the third cycle. Okay. So if it is low in the present cycle, if it goes high, then it must be high for 2 cycles, right. So this is a property of the P cell x. At a time only one P cell can be high, so more than one P cell should not be high. For P enable, we can say if P enable is high in the present cycle, it must go low in the next cycle, right. If you look at properties which involve both P cell and P enable, you see that if P cell x is low for some slave x in the present cycle, and in the next cycle it becomes high, then one more cycle later P enable must also be high. If all of the P cell x is low in the present cycle, then in the same cycle and also in the next cycle P enable must also be low, right, because P enable can only be raised after one of the P cell x has been raised, and one cycle after that P enable can be raised, right. So like this I have noted down a set of properties, right, and now I leave it as an exercise to you to write down these properties in SVA. Okay. So refer to these slides from my website and code these properties in SVA. So you may choose to use an encoding of that state machine, the state machine that I showed in the beginning, okay, this one, okay, or you may do it without the state machine also, because APB is very simple, you may not need the state machine, okay, but if you want to use the state machine, it is fine, right. Use that to do this, okay. In some cases like this, where you want to say that PW data will hold the same value as the previous cycle, you may need local variables, right, because you need to save PW data in one X, and then in the next cycle you say that the PW data in the next cycle is equal to that X, right. So try writing out this in this, okay. And the other thing that we have here is I will give you a complete set of these experiments to be done on the system Verilog test bench generation part, right, and their solutions. You can just try to run them on the system Verilog environment, okay. For the APB, I will give you an object, I will give you the test bench, complete test bench, incrementally adding these components, right. If you just run it, you will see how it works, right. So just remind me that I should pass it on to you, okay. Thank you. So with that we come to the end of this lecture.